Friends, in our last lecture, we have studied about the bending of a beam, bending moment. That concepts are useful here. Now, here we are going to discuss cantilever loaded at free end. See, cantilever is a body, it is nothing but a beam which is fixed at one end and free at the other end. See now, for this there are two cases. When the weight of the beam, weight of the cantilever is ineffective, and another B case is when the weight of the beam is effective. Today now we will see when the weight of the beam is ineffective. For that purpose we have to draw the diagram. The diagram in this way. This is nothing but the AB. This is a neutral axis of the cantilever body. See, this AB cantilever having a length L, and this A end is a fixed one, whereas at the B end we are here loading the weight W here, and due to which depression is there, and due to that depression this B point here we get B dash. Now see, the depression is in this way, this A B dash, and this is depressed through the angle d theta. See now again from this point P and Q, we will make a tangent which touches at to the this vertical line B D dash at C and at D. This is nothing but the geometry of the body, that is cantilever, where the case is weight of the beam is ineffective. Means here for the depression we are not considering the weight of that beam. See now, the same thing here, it is written AB represents the neutral axis of the cantilever which having a length L. As we discussed, the cantilever is fixed at the end A, and whereas it is loaded at B. It is loaded at B through the weight W, such that then end B is depressed into the position B dash, and the neutral axis takes up the position AB dash. Here it is assumed that the weight of the beam itself produces no bending. Now here we will consider a section P of the beam which is located this section, and which is located at a distance x from the end A. Then the moment of the external couple at this section due to the load W, or the bending moment acting on it, here simply W into PB dash. PB dash is nothing but the length of that neutral axis, and it is L minus X. Now here see, Since the beam is in equilibrium, then it must be equal to y into Iz upon r, or it is equals to y into ak square upon r, where here r is nothing but the radius of curvature of the neutral axis at P. Therefore, here just we have been written W in bracket L minus X, that is nothing but the moment, external moment of the couple, and therefore this is equals to this quantity y into Ic upon r, or it equals to y into ak square by r. This is nothing but the equation 1. Then as the moment of the load increases as we go towards the fixed end, then the radius of curvature is different at different points and decreases as we approach the point Q. Then for a point Q, however, at a small distance dx from P, it is practically the same as at P because it is a small one, and therefore PQ equals to R into d theta, or we may write that is dx equals to r into d theta. D theta is nothing but the angle POA, and see here r equals to dx by d theta. Now we will substitute the value of r. This value of r we will substitute in this equation, and we will get w in bracket L minus x as it is, y ak square as it is, and we have to substitute this r by dx by d theta. Therefore y ak square into d theta by dx, and therefore d theta now, see this d theta equals to w into L minus x bracket close, and this dx here divided by y ak square. Now as we discussed that we have to draw the tangents to the neutral axis at P and Q. These tangents will meet at C and D to the vertical line BB dash. These things we can see in the diagram, and the depression Q below P is equal to CD, and that CD means here you can see CT, this much depression, very small depression, that is nothing but the dy, that is a dy, and therefore here dy equals to in bracket L minus x into d theta. Now substituting the value for d theta, we have to substitute the value for d theta. Dy equals to what? L minus x into w. See, this is the value of dy, L minus x into d theta. Now d theta is w L minus x into dx upon y ak square here. See here, L minus x into L minus x square into dx as it is, and y ak square. See here the depression y equal to dv dash of the loaded end B below the fixed end A is obtained by integrating the expression for dy between the limits x equal to 0 and x equal to L. See here we have to integrate y equals to w in bracket L minus x square into dx upon y ak square between the limit 0 to L. And see this much quantity y w upon y ak square is a constant one, and we will take it outside of the integration sign and integral of L square minus twice Lx plus x square into dx, because L minus x square is the expansion, that is a minus b square, that is a square minus twice ab plus b square in this way into dx. And this is the third equation. We are here going to solve this integration, that is integral of L square minus twice Lx plus x square into dx. See this L square and integral of dx, that is a x, dx is a x minus twice L x square upon 2 plus x cube upon 3 means that between the limit 0 to 3. Here how this comes, this 2L as it is, this x multiplied by the x coming from this quantity, that is x square, that is 2Lx square by 2 plus this x square, this x cube by 3, this here between the limit 0 to L, where upper limit is L, lower limit is 0, and this 2 will get cancelled. Therefore this L square, we will substitute this x by upper limit L minus L square, this x square means L square, this 2 will get cancelled, L square into L plus L cube by 3. This L cube by 3, this value which we got by the integration will be put in the equation 3 is wy ak square, where wy ak square is L by 3, and see if L cube upon 3y ak square, as Ig we know that it is nothing but equal to ak square, and this WL cube upon 3yIg, and thus the free end of the cantilever depressed by WL cube 3yIg.